Sometimes using the method of joints can be quite overwhelming, especially when you're working with a trust structure that is so huge. Okay, one of the way to greatly simplify the calculation process is by identifying slender members which does not support any load. So if it doesn't support any load, it is also known as the zero force member. Okay, but if you think about it now, how can a zero force member be a useful component, be a useful feature to a truss structure when it doesn't support any load? Well, basically, the zero force member is very useful to increase the stability of the truss during construction. It can also be used as an added support in any case or in any possibility that the loadings on the truss is changed. The big question now is, how do we identify the zero force member? Okay, first step, identify the points of each joints. Sama macam method of joints tadi. And then the second step, you draw the free body diagram of the joints. The third step, if you apply the equilibrium condition or the equation of equilibrium, you can actually determine the magnitude of forces on that particular joint. So, for a zero force member, it would have a force magnitude of 0, either in X or in the Y direction. Okay, look at this truss structure. It consists of 9 slender members. So, you imagine, sebelum ni, when working with only 5 members, the solution process can be quite long kan? So, apatah lagi when it involves 9 slender members. So, one of the way to simplify the analysis process is by identifying the zero force members. In order to find a zero force member, you start at a joint where there is no external force or no support reactions, a very free kind of joint. Okay, so one of the joints in this truss structure is joint A. Joint A is connected to slender member AB and also slender member AF. If we draw the free body diagram at joint A, macam the method of joints do, there will be one force between joint A and member AB. Accordingly, there will be another Y direction force between joint A and member AF. So, if we apply the equilibrium condition in the X direction, assuming the summation of all the forces in the X direction is 0, then there is only one force exists in the X direction, which is AX. So, our AX is 0. So, from this equation, we can say that AX, which represents the force at member AB, is 0. So we can conclude that member AB itself is a zero force member. Okay, so you see, if we apply the equilibrium condition accordingly in the Y direction pula, so summation of all the forces in Y direction is equivalent to 0. So there is only one force exists in the Y direction, which is AY. So AY is equivalent to 0. So bila AY is 0, it means that the member AF is also a zero force member. So that is how you identify the zero force member in this particular truss structure. Since the slender member AB and the slender member AF is a zero force member, so we can actually eliminate these two slender member from our calculation. So you see, the truss structure becomes so much simplified. Okay, now let's look at another free joints, free as in without any support reaction or without any external load exerted on it. So another joint that we can look into is joint D. So joint D is connected to slender member DE. So we can represent the force between joint D and slender member DE with FDE like this, in this direction. Okay, accordingly, joint D is also connected to slender member DC. And we can represent the force between joint D and slender member DC with the force of FDC like this. Okay, now you see there is one sangat bengek punya force kan. So as usual, we can actually resolve this FDE into an equivalent X and also the Y direction. So in the X direction, it will become FDE sine theta, and in the Y direction, it will become FDE cos theta. Okay, now again, similarly, let us apply the equilibrium condition respectively in the x and y direction. So if we apply the equilibrium condition in the x direction, summation of all the forces in x equivalent to 0, so there is only one force exists in the x direction, which is FDE sine theta. So that is equivalent to 0. But if you look at this particular equation, in order for this expression to become 0, it would either be FDE yang sama dengan kosong or sin theta yang sama dengan kosong. But if you look at the thrust structure punya image, sin theta tak akan sama dengan kosong because the theta itself would never be a 0 degree. There is some kind of degree, angular displacement kan between beam DE and beam DC. So theta would never ever be 0. So if theta is not 0, then sin theta would not be 0. So therefore, in this particular equation, we can conclude that the FDE itself is equivalent to 0. So the force between joint D and also member DE is equivalent to 0. So we can conclude that member DE in particular is a zero force member. Okay, so now if you apply the same equilibrium condition in the y direction, summation of all the forces in y is equivalent to 0. So there are two items in the y direction, which is FDC, it becomes negative because it's pointed downward, and FDE cos theta, negative also because it's pointed downward. So these two expression is equivalent to 0. So recall from our previous equation yang sebelum ni, we already concluded that FDE sama dengan kosong kan. So kosong darab dengan cos theta will become 0. So the remaining expression, which is FDC, would be 0. So accordingly, the slender member DC is a zero force member. Okay, since we already identified that member DE is a zero force member, member DC pun zero force member, so simply we can eliminate these two slender member from our thrust structure analysis. So yang tinggal is only 5 slender members. So you see, from 9 slender members, we have identified 4 zero force member. So that zero force member we can eliminate from our calculation. So for your structural analysis, you can just proceed with these 5 slender members. Okay, so that is how the analysis of the truss structure can be simplified. From this particular exercise, we can conclude that two slender members connected to a free joint, like joint A and D, a free joint means a joint without any external load or any support reaction, then that two members connected to it must be a zero force member. So, if it is a zero force member, we can just ignore it during the structural analysis process. So that is why the thrust structure analysis becomes so much simplified. Okay, now let us consider a different kind of truss structure. This time around, you can see that the free joint can be the joint C and joint D. Let's look at joint D first. Joint D is connecting 3 members, as in member DA, member DE, and also member DC. In this case, you cannot simply conclude that all these 3 members are a zero force member. So if we draw the free body diagram at joint D, this would be the force representing member DA, and this would be the force representing member DE, and this would be the force representing member DC. So if we consider this as the x direction and this as the y direction, and let's apply the equilibrium condition in both x and y direction. So let's consider the x direction first. Summation of all the forces in x should be equivalent to 0. So there is only one force acting in the x direction, which is FDA, and that FDA is equivalent to 0. So we can safely conclude that member DA in particular is a zero force member. Okay. However, if you consider the equilibrium condition in the y direction pula, so there are two forces acting in the y direction. It would be the force from member DE and also force from member DC. Okay, so we can generate the equation of FDE is equivalent to FDC. So we cannot simply say that FDE and FDC is a zero force member. There's a magnitude going on over there, but the magnitude is the same. What we can safely conclude from this exercise is that we know that member DA is a zero force member. So we can actually eliminate member DA from our structural analysis. However, member DE and member DC have the same force magnitude. Okay, so we can actually eliminate joint D and merge member DE and member DC to become one single slender members. Okay, now if you look at joint C, it interconnects between beam CA, beam CE and also beam CB. So if you draw the free body diagram at joint C, then beam CA can be represented with a force in this direction called FCA. So the force at beam CE can be represented with this kind of force direction, while the beam at CB can be represented with a force in this direction. Okay, so if we are to consider the x and y direction similar with our previous joint analysis, then there is one sangat-bangat force direction in this particular free body diagram, which is the FCA. So accordingly, we can resolve this force into an equivalent x and y magnitude. So in the x direction, it will become FCA sine theta, whereas in the y direction, it will become FCA cos theta. Okay, so now we can apply the equilibrium condition in x and y direction. So assuming all the summation of forces in x direction is equivalent to 0, so there is only one force exists in the x direction, which is the FCA sine theta. So this expression is equivalent to 0. So from this expression, there is one element which is the FCA. It can be 0, or the sine theta can be 0. Sine theta would never be 0 because the theta would never be 0. So it will have some kind of magnitude. So in this case, we can conclude that the FCA, the force between joint C and beam CA, is the one that have the magnitude of 0. So from this conclusion, we can say that member CA is a zero force member. Okay, so now accordingly, if we are to apply the equilibrium condition in the y direction, so there are three entity or three force element in y direction. So in one direction, it would be the FCE and also the FCA cos theta. So we can put that in the left side of our equation, and that is equivalent to FCB. So now, from our previous equilibrium condition, we know that our FCA is equivalent to 0. So we can actually zero out that particular expression. So the remaining expression will become FCE equivalent to FCB. Okay, now we can conclude that member CA is a zero force member. So our analysis can be simplified by eliminating member CA. But at the same time, we know that the force along the beam CE and beam CB is equivalent. So we can actually remove joint C and just consider the entire beam E to B as a single slender beam instead. So you can see how the number of element or the number of truss member are being reduced, and in a way it really simplifies our truss structure analysis. Okay, from this particular exercise, you can see that the original truss structure consists of 7 slender members interconnected to one another. So by identifying the zero force member, the truss structure can actually be simplified into a 3 slender member kind of analysis. So as you can see, solving for a 3 slender member kind of structural analysis is much more easier and convenient compared to solving for a 7 slender member kind of structure. Okay? From the explanations given earlier, I believe you can proceed with this particular example on your own. Okay? So if you try to do this on your own, you should identify the zero force members to be member GC, member FC and also member FD. Okay, so all the best.